All right, welcome back to Multigrid Methods. Today, we're continuing on in this section, multigrid error transfer matrices in multiplicative form. So this is material from Chapter 8, which is where we currently are. This is it for Chapter 8. So this is a single slide deck that we will finish today, and then we're going to move on into Chapter 9. So I've updated chapters 8 and 9 on Canvas, both in the slides and in the lecture notes, so you can go get the latest there. And I've also updated the codes, so if you're looking for the codes, those can be found in the GitHub repository. So updates for the lecture notes, the slides, and also the codes. Last time we proved, I'll put proved in air quotes, I guess, this theorem. We were kind of blowing through it very quickly at the end of class. So the idea was that we were trying to show that the error transfer matrix for the multigrid V cycle, in the case that we had a symmetric one, symmetric V cycle means M1 equals M2 equals some common value M, and the V cycle is indicated by choosing the parameter P equals 1. Then we proved that the error transfer matrix can be expressed in this long form. And so you basically got the error transfer matrix bracketed by these smoothing operations, and then all these errors in, I'll just call these things T matrices for short, these errors in these T matrices that we define, which are a combination of coarse grid projection and also smoothing in some sense. And then you go all the way down to the coarsest grid. We have an error in coarse grid coarse grid risk projection. And then we come back up. So explained this last time. The key feature of this was showing that we can essentially write this function MJL, where MJ was defined as, I apologize, go back here. MJ was this guy, which is this core of the error matrix. Okay, so it's the thing which kind of sits in the middle. And we want to characterize how that thing looks, and we successfully characterize how it looks. We could show that it satisfies this recursive identity. So MJL equals these errors in these T matrices times MJ minus 1L. So this is the one level down. And therefore, what we need to do, or what we did do whenever we proved the structure of the error transfer matrix, if we look at the error transfer matrix at a generic level L, it involved ML minus 1. But this little identity here allows us to ratchet this middle object down 1. Okay, each time we go down 1, we gain 2 more errors of T matrices. And until we get all the way down to the coarse grid risk projection, all the way at the 0 level, or the base level. Sometimes I call this the root level. And then, of course, you've got T matrices bracketing this on either side all the way down. And the key is observing that the error transfer matrix can be written as this ML minus 1L matrix right here. And on either side multiplied by these error transfer matrices for our smoothers. All right. So that's all there is to the proof. Of course, there were a lot of complicated details in between, but that was the basic idea. So we proved this last time. And let's see how knowing this, or I should say, how knowing this fact is beneficial for us. Well, the first thing to observe is that we can prove therefore, that our error can be written as a product of matrices which look like this. I minus B is an iterator matrix. I should say IL minus BL times AL, a product of a bunch of those, where these BLKs form a family of iterator matrices. So if you look back at the structure that we just proved, um, we essentially did exactly that. Even the K matrices, by the way, so the KL matrices have that form, although we didn't write that explicitly. These are IL minus SL AL. The TL matrices can also be written in the same way. So the TL, or actually the I minus TL matrices. So IL minus TL, blah, blah, blah. That can be written as I minus some iterator times AL. So whatever that is. And so we have this for all of those matrices. So basically what we've just shown is that our error transfer can be written as a product of error transfer matrices. Okay, simple error transfer matrices. So this gives another proof that the V-cycle algorithm is multiplicative GLIS method. And all you'd have to do then is discover what are these iterator matrices. Well, it turns out in our case, you can just read off the iterator matrices by definition from here. So if you've ever wondered what are those products of iterator matrices, then you can read them off by figuring out, well, decomposing what this guy should be. Okay, and there's one here. There's going to be an iterator matrix here. So basically, I want to take each one of these and break them apart into something like a B times AL. And again, B times AL and B times AL. Of course, the B's are different in each of these cases. But you can do that in each one of these cases. And this shows that this is a multiplicative method. It just is saying, well, what you're doing is using a bunch of different iterative methods in a multiplicative way. And this is exactly what we described in chapter 1, way back in chapter 1. And that's basically why we went through that exercise. This gives an independent view or proof that we have a multiplicative GLIS. Now, if you have a multiplicative GLIS, then the whole thing is a GLIS. In fact, whenever I can write something like this, then I know that there's one iterator matrix so that I can write the whole thing like this. I can write this with one all-encompassing iterator matrix, BL. So for those of you who recently come to office hours, I've taught you how to figure out what this BL is by another method. So the way to find it is not to multiply this guy out and then extract it that way. That's a very hard way to do it. There are other ways. However, we know that for every multiplicative method, we can get a B matrix like that. So that was a little theorem or theory that we developed in chapter 1. But in any case, this gives us an independent proof that our V-cycle method is a multiplicative linear iterative scheme in the sense that we discussed way back in chapter 1. Now, this one's kind of a simple corollary, at least I hope you see it as simple, if we use a fact that we learned a while ago. So let's consider the one-sided V-cycle, where we only do pre-smoothing. So pre-smoothing simply means that we are going to have M1 equals M, which is greater than 0, but all the M2s are going to be equal to 0 exactly. So this is what we mean by a one-sided V-cycle algorithm with only pre-smoothing. Then it's fairly easy to see just by the considerations that we did in the last proof to show that the error transfer matrix for that case consists of only this portion of that decomposition. So what's missing is the left-hand part. All you have is the right-hand part. Starting at the course level, I have these T matrices only, and only this error transfer for smoothing. So I hope that that's clear, and that's because all of the T matrices that are going to be on the other side are just going to be zeros. Okay, all the T matrices on the left-hand side are going to be zeros. Conversely, if we only have an algorithm with post-smoothing, so does this make sense? In some sense, it does make sense. And we'll see actually that it actually works and it converges. So if we only have post-smoothing and no pre-smoothing, then we're going to have an error transfer matrix, which looks like this, a product of these matrices. And of course, all the stars are on the left-hand side, the unstars are on the right-hand side. And now the thing that would have appeared on the right-hand side, those M values are all 0. And so I just get a bunch of identity matrices which multiply each other. And so that's why the error transfer matrix for the one-sided post-smoothing algorithm looks exactly like that. Well, now, if you remember that this matrix times itself is just itself, because this matrix is what we call a projection matrix, then if I multiply EL post times EL pre, you get right back to the original error transfer matrix for the full V cycle. Okay? Now, now look at this string of matrices and look at this string of matrices. And it's not too hard to see that each one of these has a correspondent, which is the, if the M's are truly the same, has a correspondent which is just its adjoint with respect to the AL inner product. So that's what star means. Star means adjoint with respect to the AL inner product. At least in this case it does. So each one of these has a correspondent. This is the adjoint of this. And all the way down until we see that this guy is the adjoint of this. And this always is self-adjoint. So EL post star is equal to EL pre. Pretty easy to see that. At least I hope it is. And just keep in mind that the adjoint operator, has the same properties as transpose does. If you take the adjoint of a product, it's product of adjoints, but in reverse order. Okay. Finally, the EL matrix is itself self-adjoint. Actually, we proved that a long time ago, but it's easier to see now that you know that that this is true. So now that thing that took us a long time to prove and very, very complicated is very easy because we know how to express these EL pre and EL post matrices separately. And we know that they are adjoints of one another, according to this statement. And therefore, EL has to be self-adjoint because of this property. And furthermore, it's not just self-adjoint, it's got to be self-adjoint positive semi-definite because of this property here. Okay, in fact, this is just EL pre star times EL pre. So it's easy to show that in or with respect to this inner product, this guy is self-adjoint positive semi-definite. So there's no real proof for this. It truly is, I think, a corollary. You just put together all the facts that we've learned up to this point. All right. So here's the theorem. Both the one-sided methods converge for any M, provided Richardson's method is used for smoothing. And remember, we're in the context here, I think I said this, of the finite element method. So we, of course, therefore have all the strong approximation property that we need. We have the Galerkin property that we need. And now that we have smoothing, we have all the smoothing properties that we've discussed previously. So we know that the full V-cycle method converges, but now we can show quite easily that each of the one-sided V-cycle methods also have to converge. Here's the cute little proof. So we showed earlier when we were in chapter 5 that the V-cycle, the symmetric V-cycle converged. Okay, so the symmetric V-cycle has the standard error transfer matrix EL. And we showed that in the AL norm, we had this contraction rate. So how do we know that this is a contraction, by the way? Well, we have, of course, we know, of course, that this guy here is a constant, which I should have pointed out is our gamma. This guy is less than 1 because this is a number and this is the same number, and we're adding a number, a positive integer to it. So the whole thing has to be a fraction less than 1. Moreover, it has to be a fraction less than 1, which is greater than 0. So the way we can do this is the easiest way to do this is to prove that this guy is less than, it should say, I need to change this. It's a typo. So either I should say it's operator norm is less than that, or I have to add this. So either I can say, so either we can show that EL free in the operator norm is less than gamma, or we can show this for all UL. So I think I need to add that. Okay. They're effectively equivalent. So this is what we're going to try to prove, this with this correction added in. Gamma times the AL norm of UL. We want to show that. So how do we do that? So let's take this guy specifically, the EL pre matrix, multiply it times an arbitrary U. Well, this is equal to that product, right? In this AL inner product. It's the AL inner product of this vector against itself squared, okay? Or not with the square. The norm squared is the inner product of the vector with itself. Now, we can take either one of these guys and move it to the other side. So you get to choose. Let's take this guy and move it over here. When we do that, it picks up a, we pick up the adjoint symbol. We're taking its adjoint with respect to AL. But now we know from the last corollary that this product is just the full error transfer matrix for this symmetric V-cycle. So this is the one-sided V-cycle. This one is the symmetric V-cycle. But notice that this is no longer a norm, right? Or a norm squared. This is something a little bit different. How can we deal with this? Well, let's use Cauchy-Schwarz. Cauchy-Schwarz is a valid inequality for any inner product. And we know that this is a bona fide inner product. So we can use Cauchy-Schwarz on that to show that that's less than the norm of U in the AL norm and times the norm of ELU with respect to AL. This, of course, we proved was less than this value here. So we can multiply this times that and get the norm squared. But so look, we started out with the norm squared and we end up with the norm of UL squared. Now all we have to do is take the square root of both sides. So we take the square root and we get this object here. All right, so that's the gamma that we want to use in this proof. Okay, so I guess I should, if I wanted to call that gamma, this should be gamma squared. So let's not do that. Let's just call this one, this gamma is the thing we're looking for. And it turns out the gamma that we're looking for is precisely the square root of that. So we're going to show, and ultimately do show, that gamma is equal to the square root of CO over MCO plus CO. And of course, this guy here is again a number which is greater than 0 and strictly less than 1. If a number is strictly less than 1, then the square root of that is also strictly less than 1. All right, so that's the proof that at least the pre-smoothing version works. I guess I didn't say for how you do the post-smoothing. I probably should have added a couple of words, but the post-smoothing is done exactly similarly. So we only prove it for the pre-smoothing, but the post-smoothing one-sided V-cycle also works, and I'll leave that. That's a nice homework exercise, actually. I'll add that one. Very easy, though. So EL post is done And now how do I spell logos? I forget. I think I might be missing a U. Am I missing a U there, guys? Maybe. Well, not a huge deal. Okay, so that one can be done analogously, however you spell it. All right. So let's finish up this section with a couple of theorems whose proofs I won't do, but I'm hoping you guys can do. So for the V-cycle algorithm with only pre-smoothing, so that again is an algorithm which is our standard, one of our standard ones, and it's defined by setting M1 equals to some value M, M2 equals 0, and choosing P equals 2. That gives us our basic W cycle. Then the error transfer matrix can be expressed as some matrix FL times, the error transfer matrix for the W cycle. Okay, so this is the error transfer matrix for W cycle here. Could be some complicated, beastly looking thing, whatever it is. It should be just some matrix times the error transfer matrix for the one-sided V-cycle method. Okay, so that's a curious fact. Um, where this FL matrix is a square matrix that has this following property, that the AL norm of FL is less than or equal to 1. So, how can this be so? Well, it kind of makes sense because if we already know, so let's look at this in a kind of um, high level setting. We already know that this error transfer matrix should be convergent and contractive. We also know that we proved this, that this guy was convergent, therefore contractant. So if this product is true, then this guy, so that's kind of the first assumption I'm making. If this product is true and equal to that identity, that this identity is true, then this matrix can't be amplifying error. It has to be contracting error. And because if it amplified error, then it could screw up the convergence of this guy. For example, this guy could be a matrix which is, let's think of it like this. Remember this thing called what is that called? It's this property here. And you guys will probably yell at me for forgetting the name of it. Okay, I regained it at the end. Submultiplicativity, right? So it's going to be FL EL pre AL. All right. So if this guy, so it's kind of the logic isn't exactly perfect, but the idea is correct. So if this guy was amplifying, but we know that this is contractive, then the product of the two things might not be contractive. But we already know that the W cycle does converge whenever we use Richardson's method, at least. So it must be that this guy has a is overall contractive. Otherwise, the product of the two matrices couldn't be contractive, and we know that it is. So that's kind of a hand-waving argument for why this makes sense and should be true. It's not a rigorous proof in any way, shape, or form. So again, we should be able to show that the error transfer matrix for the W cycle is equal to a product of some matrix times the error transferred matrix for the one-sided V cycle. And this matrix should have an AL norm, which is less than or equal to 1. So again, my little argument here is not in any way, shape, or form or proof. It's just kind of a high-level way of looking at it. The proof is left as a homework exercise, and I'm sure I'll be getting a few of you coming to office to ask about that one. All right, now for the symmetric V-cycle algorithm, that is P equals 2, M1 and M2 equal and equal to some common value M. Then the error transfer matrix for the symmetric W cycle. So that case you do pre-smoothing and post-smoothing. We did not address this one in chapter 5, at least with the material that we went through. We only did the one-sided V cycle. It's it's not hard to show that the two-sided V cycle also converges, but we just didn't tackle it. So now we're going to address that question. Well, the W cycle should be, or the error transfer for that should be something which looks like this. EL pre-star, so this is the adjoint with respect to AL inner product, times some matrix D times the EL pre, where EL pre was, as before, just equal to this product. So it's the right-hand product only. And like before, this DL matrix should be something which is not amplifying in the AL norm. Okay. Again, you can kind of put together a hand-waving argument about why that's so, but the devil, I guess, are in the details. This algorithm converges if the symmetric V cycle converges with the uniform contraction rate gamma. So if we assume that, let's see, if we assume that this guy has a contraction like that, then this matrix will also represent a contraction. I didn't put a rate there. I probably should have. I think the rate is going to be the same, in fact, for the W cycle. So I'm going to make a conjecture that I want you guys to check when you go through this problem. Is it true that, and I don't know actually. So I'll put a question mark here. Is it true that the contraction is something like this? Good question. I think so. Um, probably, um, and probably not too difficult to prove if I'm guessing. But I didn't go through the details of it, so I'm going to leave that. At least I haven't gone through the details of it lately. So I'm going to leave that for you guys as an exercise. All right, that's it for chapter 8. Basically, all I wanted to do was show that there was a new way of looking at the error transfer matrix. And this way of looking at it confirms conclusively that that the symmetric V cycle and the symmetric W cycles are effectively multiplicative general linear iterative schemes. Now, we didn't exactly show it for the W cycle. It's not quite as easy, and that's because this matrix in the middle here is not exactly we don't know what its structure is just by this theorem. We do know that this has the structure of a multiplicative error transfer matrix, but we don't know what this DL might be. So we did, however, show that the V cycle is definitely a multiplicative general linear iterative scheme. And we showed that the one-sided V cycle and the both using the pre-smoothing and the post-smoothing types of one-sidedness, both of those algorithms also converge. And then we talked a little bit about or saw how you can use that to decompose in some way, not completely decompose because we don't have an exact form for this guy, the symmetric and the one-sided W cycle algorithms as well. All right, so I'm going to end there in chapter 8, and you guys can turn your cameras back on and I can take any questions you have. All right, so now we're getting started in chapter 9, and the rules again are going to be the same as before. We're going to be using the finite element method as kind of the backbone here. Now, we really haven't talked about anything else. Finite element method has been the only real discretization we've hit upon. We did say in chapter 3 that the finite element and the finite difference method were equivalent in 1D. But in chapter 7, which we skipped for now, which we will come back to, and is looking more like we're going to come back to that at the start of next semester, when we go into chapter 7, we really are going to discuss a new framework for discretizing equations based on the finite difference method, and specifically the cell-centered finite difference method. So there is variety coming. But in chapter 9, like chapter 8 and chapter 6 before that, we used and will use the finite element framework specifically. So when you think about that, in the back of your mind, you're going to think about, well, my stiffness matrices all satisfy the Glerkin condition. Fine. I know that the strong approximation property holds fine. For this chapter, it's mostly going to be important to think about the stiffness matrices as those coming from the finite element setting. Now think about how we define the stiffness matrices for the finite element setting. So we define those via a basis. Remember, we had a basis for BL, which was our finite element space. And then we said, well, we had this bilinear form called A laying around, and A, our stiffness matrix at level L, if we looked at the I and J components of that guy, were defined as, so this basis was a set of vectors called psi L. How did I write it? Psi Lj, I think. J equals 1 to NL. Then we said that the elements of the stiffness matrix, the entries of it, are equal to A psi L J psi Li. Okay, for all I and J. And just keep in mind, I told you before, we reverse these indices, right? So this first index becomes the second, and the second becomes the first. So that's the main thing we're going to be using here, main technology. We're also going to be really dwelling on the fact that we know what this basis looks like. This was the Lagrange nodal basis of hat functions. And so just keep that in mind. That's what we really need to survive in this chapter. Now, why do we talk about additive methods, and what are additive methods? Well, additive methods mean that we're going to write a GLIS, which is something like this. UK plus 1 equals UK plus, I think it's the residual, right? So it's F minus A times, I forgot my B matrix. Don't want to forget the B matrix. UK. We can put L's here, I guess. Everybody gets an L. So an additive process means that my matrix, my iterator matrix, can be written as a sum of iterator matrices. How many do we want to do? I don't know, R of them. And like I said, if that's true, then I minus BL times AL is just equal to IL minus BL1 times AL. It's very easy to see this. Plus dot 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 up to IL minus BLR AL. Very easy to see that. So if we have an additive process, we have an iterator matrix with splits like this. Now, additive processes, we said just a minute ago in the discussion offline, that those are highly parallelizable processes.
Dr. Wise,
Yeah.
how do you get that IL minus BLAL? How would the IL be repeating so many times?
Let's see. Good question. Yeah, if I put it in there just by itself, it doesn't repeat, right?
Yeah, unless you do like R times IL.
I'm missing something key here, but maybe one of you can go back to chapter 1 and see that discussion. I'm missing something. I'm missing something kind of fundamental. I'm not sure what it is actually, but I see your point exactly. So if I simply take this definition and dump it into there, it doesn't give you this, right? It gives you IL minus all of these guys. So yeah, maybe I have to break that up into, I have to, I could split this up into by dividing by R, right? So let's do that, right? So if I put 1 over R there. So what I'm gonna, yeah, let's write that. That's fine. It's not exact. I guess I didn't exactly make this argument in this way last time. Let's see, but I have to put it inside, don't I? So I guess it doesn't exactly have the structure I was thinking, but it has almost the structure. Now, if I multiply this whole thing times R, right, then this guy's going to get R times that, etc. I can remove that. I can remove this guy and throw the R onto this one. So I can effectively make it look almost like that, but that's a good point that you made. It doesn't exactly break down like this. It's more like that. Okay, do you agree with that?
Yes, that makes more sense.
Yeah, well, it makes mathematical sense, I guess. The other thing I wrote doesn't, but yeah, you're exactly right. This still has the structure of something which looks like what I want. So I'm okay with that. I'm okay with that. In fact, I guess I can write it as, if I want to keep it exactly like this, I could say, and thanks for pointing out the error. So what did I say that was? That was if I multiply by R, like no, I'll skip it for now and maybe I'll write up a note about it. But I did discuss this in chapter 1. This and this are correct, but this representation is not exactly right, but it's also, like my friend Abner says, it's morally correct. It's the right structure. But good point, good point. In any case, so additive processes can always be done in parallel, whereas multiplicative processes cannot. So we're going to devise a method of creating a linear iterative scheme which has this breakdown. And we're going to create something called an additive preconditioner. All that means is we're going to make an additive iterator matrix that's going to be worthwhile in some sense that I'm going to explain. Okay, lots of words here. I'm not going to try to read through all of that. What I will say is I will pick out one thing which is more glaring than the others. We're going to pair preconditioning with the conjugate gradient algorithm. So if you want to know about conjugate gradient algorithm, most of you I have used in numerical analysis with this concept. We talked about it in 571 quite a bit. Um, and we talked about this idea of preconditioning, but I never gave you any really good examples of what good preconditioning matrices could be or should be. And the reason why is because it requires a lot of deep theory and technology to invent and talk about good preconditioners. Well, it turns out that this iterator matrix that we have devised or will devise is what we call a preconditioner. It's going to turn out to be a symmetric positive definite matrix, which can be paired with the conjugate gradient algorithm to do some processes in what we call parallel. And that's precisely because it's going to be given to us by some additive process. So our preconditioner is going to be invented so that it has this decomposition, BL1 dot 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 plus PLR, something like that. we're going to show that this preconditioner is symmetric positive definite, and it can be therefore paired with the conjugate gradient to make an efficient algorithm for solving certain certain equations, namely the equations that we're using as our kind of prototype, the equations resulting from discretizing the Poisson problem via the finite element method. So that's the plan for this chapter. Figure out how to write an additive preconditioner in this sense in order to pair it with the conjugate gradient method to get an efficient solver. So let me see if I can do a decent job of explaining that. And if not, then I'll try to answer your questions in real time and then also update the notes with some better ideas, and we'll see how this works. Well, the way we're going to create additive preconditioners, again, additive preconditioner means the iterator matrix has this type of decomposition, is we're going to use what's called a subspace decomposition to do it. But you have no idea what a subspace decomposition is, so let me try to explain in a kind of general way what a subspace decomposition is, and then I'm going to show you in a very specific way what a subspace decomposition is for something like a finite element vector space. So here's my abstract. So if any of you are in algebra or you really love linear algebra, I know some of you just really love linear algebra. If some of you are kind of in an abstract algebra, I don't know if any of you are, and you're taking this class to see what numerical analysis can be used for, is good for, is in any way interesting. You might like this structure because it's highly abstract, and there's a lot of just abstract linear analysis and in particular linear algebra in this. So here's my setting. I want to take my standard primordial vector space Rn, and I want to basically break that into a bunch of subspaces in a reasonable way. So what I'm going to do to break it into subspaces, and this will become clear with examples, is I want to introduce some kind of matrices that operate from the subspace back to the parent space. So this is always going to be our parent space, and then we have these other subspaces which are going to be decomposed, into which this is going to be decomposed. Now, let me give you a very basic way of decomposing these subspaces. So how can we do this? Well, we could think about Rn, let's see, as broken up into, essentially, let's say n is even. We could break it up into Rn over 2 plus Rn over 2. In the same way that we could think about R2 is really just a way of putting the real line together with itself. Okay, I'm going to write plus with quotes around it. What do I mean by this plus? So it's really like two copies of R1 put together, right? And that's kind of clear. Well, that's kind of a subspace, a very simple subspace decomposition of R2 into two real lines. We can do that with any Rn. If n is even, we could break it into Rn over 2 and Rn over 2. We could split them by halves. We could break this into R1 plus R1 plus R1 plus R1 n times. So that's another way we can make a subspace decomposition of Rn. But so let's try to formalize that, and I'm going to do that with some examples and some definitions, some theoretical definitions. So I don't blame you if the theoretical definitions go over your head, but the examples will pull them back to earth. So suppose that we're thinking about Rn, we have the dimension of Rn being n, of course, and suppose that mj, j equals 0 to L, is a collection of integers that have this hierarchical form. So m0 is the smallest. It's not necessarily 0, it's just some counting number indexed by 0, which is less than or equal to m1, which is less than or equal to mj, which is less than or equal to ml. This is the maximum level, which is all of which are less than or equal to n. Okay, so the previous example I gave was a good one. So if I take R2 and I'm going to think about breaking it into R1 quote plus R1, if that could be done, then what I'm thinking here is that n is equal to 2, n0 is equal to 1, and n1 is equal to 1. So both of these numbers are greater than 0, and both are less than or equal to n. Now, we're going to create these matrices called prolongation matrices, a name which you've heard before, which are going to be a collection of J matrices that are in Rn by Mj. So you should think about it like this. They have a lot of rows and not so many columns. So they're tall and skinny matrices, just like before. So that's what we call a prolongation matrix. We're going to call them prolongation matrices as long as they are full rank. So the rank in this case is going to be Mj, okay, because all of these M numbers are less than N. So let this be a set of prolongation matrices. We say that assumption SS1 holds. SS means subspace. SS1 holds. Or equivalently, we're going to say that that collection of prolongation matrices supports a subspace decomposition of Rn if and only if for every U in Rn there exist vectors Wj in Rmj such that U can be written as the sum of these vectors, Qj times Wj, from j equals 0 to L. All right, so these are matrices, these are vectors, and when I multiply these two things together, everything is joined up just right so that this product lands me back in Rn. So I'm going to add a bunch of vectors in Rn to get back to my original U, which is in Rn. So here's where U starts. It has to be for every U. I have to be able to do this. I have to be able to do this so-called decomposition. So this is what we call subspace decomposition. And you can think about it as being a bit like this, but let me give you an example. So this was what I would consider as the simplest possible example. So let's take Rn, and we're going to think about what does Rn look like? You can think about them as collections of vectors, so that look like v1, v2, up to vn, right? So what I'm going to do is I'm going to think about splitting this in basically n copies of R1, where each of those copies in R1 is going to have these coordinates in them, okay? So how would I define my Q matrices and my W vectors given some arbitrary U to make this happen? So what I'm going to do is I'm going to set up these Q matrices. They're just going to simply pick out one element of that vector, or of the vector U ultimately that I want to use. So the vector that I want to use for this very simple example is going to be for each j. Remember, j starts at 0, and it's going to go up to L equals n minus 1. N is the definition, or is the dimension of the parent space that I want to break things into, or the space that I want to break apart. So Qj starts at 0. The first Qj that I want to use is just going to be the canonical basis vector 1 for j equals 0. For j equals 1, I want to use the canonical basis vector e2, and so on and so forth. So in general, ej plus 1 is what I'm going to use for Qj, and that has a 1 in entry j plus 1. Now, suppose now that U is arbitrary. Then I'm going to take as my WJs, that's what I have to pick for each U. For WJ, I'm going to take that to be equal to UJ plus 1. Okay, this is the coordinate in position J plus 1. Then it's easy to see that this is going to hold. Okay, well, you might be confused by the definition, so let's work this out. Suppose I have U1, U2, U3 as an example. So all this is saying is that I'm going to have E1 times U1 plus E2 times U2 plus E3 times U3. That's all it is. That's the case where n equals 3. N equals 4, you would have the sum of 4 vectors, but that's the structure. Now, you might object and say, foul, these guys are not matrices. But remember, they are matrices according to the definition that we're using for this entire book. And we're thinking about this column vector as simply being a matrix which has one column. It has a bunch of rows in one column. So it is a vector, true, but it is also a matrix. And you might say, well, this guy here is not a vector, right? So that might be your second objection. And I would say to that, well, it is a vector. It's a 1-by-1 vector. So all I need to have is this product has to be a vector of length 3 because I start with R3. And this one as well has to be a vector of length 3 and this one as well, so that when I add them all together, I get a vector of length 3. But what I really need is when I add them together, I get back to my original vector U. So this is a simple example, probably the simplest way I can do this decomposition. And really, this is like saying that R3 is going to be written as R1 plus R1 plus R1. I can't really add those spaces together, but in a sense I can. All right, so let's go on to a more complicated example. So this is the first definition that involves what we call a hierarchical basis decomposition. So for those of you who are good at solving puzzles, I want you to pay attention and see if you can figure out immediately what is the general structure that I'm trying to introduce here. I'm going to do two examples. They're going to be slightly different. If you want to, I suggest write this down as I'm going through it if you want to try to guess at this structure. So again, this is what we call a hierarchical basis decomposition. We're going to try to decompose, again, Rn in a bunch of ways. Now, in this case, n is equal to 7. And we're going to think about 7 as being 2 to the third power. Of course, that's 8 minus 1. That gives 7. This is reminiscent of what we were looking at, the dimension of the spaces for in chapter 3 when we were looking at the finite element spaces in one dimension. They were always powers of 2 minus 1 by our convention. In this case, we're going to take L to be equal to 3 minus 1. So I'm trying to foreshadow what we're going to do in the general case. We look at this, that's a power 3, subtract 1, we get 2. So we're going to use 3 total levels, 0, 1, and 2. 0, 1, and 2. So note in this case, I'm going to take m equals 1, m0 equals 1, m1 equals 2, and m2 equals 4. And those numbers add up to n. So just add them up. 1 plus 2 plus 4 is 1 plus 6, which is 7. And that is, of course, the dimension of my space. This is the typical feature of the hierarchical basis decomposition. All right, now here's where it really gets a little bit puzzling, and see if you can figure out what to do. I'm going to use, for Q0, I'm going to use E4, just E4. So that's a matrix of size 7 by 1. So this is the canonical basis vector of order 4 or index 4 from R7. So this guy is 7 by 1 matrix. What about Q1? I'm going to take Q1 to be E2 plus E6 and see if you can figure out the pattern here. So this one is going to be the canonical basis vector of index 2 and this one of index 6 from R7. So this Q matrix has 7 rows and 2 columns. And Q2, I'm going to take E1, E3, E5, E7. So this matrix is in 7 by 4. Of course, it's mostly zeros and it has a few ones. So that's how I'm going to choose the Q matrices. How do I choose the W vectors given some arbitrary U? All right, so I'm going to take an arbitrary U and I'm going to grab for W0, I'm going to take U4. For W1, I'm going to take U2 and U6. And for W2, I'm going to take U1, U3, U5, and U7. So look, so a typical U vector has all of those numbers in them, right? All those entries, U1, U2, U3, down to U7, all of them. And so this guy, he gets the middle one. And then this one gets 2 and 6. So this one and this one. And then I've gobbled up all of the even entries now. All I'm left with are the odd entries, and the last one is going to get all the odd entries, 1, 3, 5, and 7. Now, if you notice, these indices here, 4, 2, 6, 1, 3, 5, and 7, correspond to these numbers here, 4, 2, 6, 1, 3, 5, and 7. And it's not too hard to see that when I do these multiplications, Q0, W1, I'm going to get a big vector which looks like this, mostly zeros, right? 2, 3, and then I have a 4, 0, 0, 0. That's the first one. What about the second one? That's going to be Q1 times W1. That's just going to give me 0, U2, 0, 0, 0, U4, no, sorry, U6, and then finally 0. And then what about the last one? The last one is going to give me these entries, but this Q matrix is adding spaces. Remember, it's doing what a projection matrix does. It's taking something from R4 and it's going to broadcast it up to R7. And so that one is going to give me, let's see, U1, 0, U3, 0, U5, 0, U6. No, U7, right? And that, of course, gives me back the U vector that I started with, the general U vector. So maybe you can start to see a pattern of how I'm doing this. Of course, I'll explain more later, but it's fun to see if you can guess the pattern. So I'm going to end with this example. Let's see if you can determine the general pattern from this one. This one I'm gonna throw a curveball to you because I'm gonna set n to be equal to 3 times the power of 2 minus 1. So that number is going to be 3 times 8 minus 1, 24 minus 1, 23. I'm going to set 3 levels. The L in this case is exactly equal to that number, curiously. And I'm going to choose my M numbers, the sizes of these decompositions to be 2, 3, 6, and 12. And I notice once again that 23 breaks into 2 plus 3 plus 6 plus 12 equals 23. So, and I claim that this general pattern can be repeated for any odd number, but it's mostly interesting for any numbers which have this structure. Let's say a prime times 2 to some power minus 1. Now, here's how I'm going to choose my Q matrices. The last one, of course, is going to follow the pattern of the previous. It has all the odd number ones. So there are 12 odd numbered indices. What about the 0 order one? Well, that one's going to have 2 elements, 8 and 16. The next one, level 1, is going to have 4, 12, and 20 as indices. Now, each one of these guys are canonical basis vectors coming from R23. Okay, so this is a really tall, this from here is a really tall and skinny matrix. It's got 23 rows and only 2 columns. What about Q2? It's going to have these 6 indices, 2, 6, 10, 14, 18, 22. Notice that once I've gotten up to Q2, I've taken care of all of the even indices. Okay? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. And the last matrix Q is going to have all of my odd entries. Okay, so there are 12 odd entries. So this matrix is size 23 by 12. And here's how I'm going to break down U. So if you give me a generic U that has 23 components or entries, then here's how I'm going to break that down. I'm going to take my W0 vector to be 8 and 16. Notice that that's 8 and 16 there. entries 4, 12, and 20. 4, 12, 20. 2, 6, 10, 14, 18, 20. 22, I meant to say. And then the last one is all the odd indices, 1, 3, 5, 7, all the way up to 19, 20, 21, 23. So I've broken this up into effectively 4 subspaces. 23 is broken up into 4 subspaces, and I can reassemble my vector U through these decomposition vectors, my subspace decomposition vectors, by doing it or adding up these vectors. And these are precisely crafted so that they have the same structure as the last example. I'll let you work this guy out. So see if you can come up with these 2 examples. What is the general structure of a hierarchical basis decomposition if I have a number which is something like this? So it's going to be r times 2 to the s power minus 1. Okay, so this is almost an even number. It's odd by just subtracting. Well, every odd number is almost even, I guess you could say, but it's almost a number which is some r times 2 to a power. Okay, it's off by 1. All right, so I'm going to end there and I can take your questions.